Good evening. We use batteries in almost everything, from pacemakers to pocket calculators, from cars to satellites. Tonight, we'll have a closer look at a lithium-ion battery and what's needed to keep it going. So, let's start tonight's episode on building a lithium-ion battery charger on the Technomora channel. In a previous episode, I told you I would build a battery charger for a lithium-ion battery pack, pretty much like the one I'm using here. Okay, and I want to say from the outset that if you're going to build the same self-charger that I am building, you do so at your own risk. I'll say exactly why I'm saying this, because there's a very good reason. A lithium-ion battery is a very powerful energy source. However, it is also a little bit of a monster, okay, because it is built from very flammable products, and to top it all off, the products that are in it, so not only the lithium and the carbon and some rare earth metals and stuff like that, there's also electrolyte in it, which is rather flammable. And as you all know, lithium is extremely flammable, and has the unfortunate tendency to catch fire when exposed to oxygen and enough heat, and not even that much heat. In fact, it's a well-documented fact that lithium-ion batteries, when say exposed to sunlight, harsh sunlight, and they are a little bit damaged at their surface, so meaning that the surface is damaged and oxygen can penetrate the battery, they will catch fire extremely quickly and extremely intensely. Okay, so the flames are incredibly hot and will incinerate anything in the neighborhood of the lithium-ion battery. Now, you might say, oh, if that's the case, why do they use a lithium-ion battery at all? Well, it's a little bit like Jekyll and Hyde. As long as the battery is treated correctly and works properly, and you charge it properly, the battery will deliver an enormous amount of electrical power. Well, enormous, that is, in relation to its size. Okay, so size for size, if you would say burn the same amount of gasoline as the volume of this battery does, it would the battery would deliver as much, and if I understood the chemistry a little bit, even a little bit more than the same amount of gasoline would burn. Okay, so you can imagine that such a small pack, yeah, if I lay my finger next to it, you see it's not really that big, can deliver quite a punch in electrical capacity. Okay, and that is one of the reasons why we have lithium-ion batteries at all. Now, like I said, lithium-ion batteries are a little bit of a monster, and you need to treat them nice. And that, of course, originates from its unique chemistry. Okay, so it is built around a lithium compound and a non-water soluble electrolyte, okay, which will facilitate the conduction, or the movement rather, of lithium ions inside the battery pack. There are only a few things we need to remember of its chemical setup to build a charger, because the way the charger works is very much dictated by the chemical makeup of the battery itself. So let me explain a little. A lithium-ion battery needs to be kept at a specific charge to be able to perform correctly, let's say. And what I mean to say by that is that the typical voltage of a lithium-ion battery cell, is around 3.7 volts. Okay, it can be a little bit above that or a little bit below that, but the thing is that a lithium-ion battery cell really needs to be charged at a very specific voltage. So in our case it's around about 3.7 volts. You could go to 3.85, or you could go as low as 3.5 volts, but not very much beyond those voltages. And the reason is very simple. If you go above, say, 3.85 volts, you will damage the battery. Okay, so it will literally start to decompose. You could say dissolve in a sense. So yeah, I wouldn't advise overcharging the battery, okay, because then you get back to the territory where I warned you will be confronted by a very ugly animal. Okay, so if the battery starts to heat up and you feel it heat up, I mean literally, if you put your hand on it and it starts to feel warm, well, that means the battery is either being overcharged or the battery is bad, in which case I would advise you to not longer use it. If on the other hand you discharge the battery too much, meaning that you go well below 3.5 volts, which is, let's say, a minimum sort of voltage for a lithium-ion battery. So in any case, if you go below 3 volts with a lithium-ion battery, you irreversibly damage it, meaning that the chemistry in the battery will make it so that the lithium will be bound in such a chemical sort of bond that it cannot be charged again, and therefore not discharge any voltage either. So yes, you really have to treat lithium-ion batteries nicely. In any case, knowing that, we know that we need to build a charger which charges the battery at a certain voltage. So in the case of one single lithium-ion cell, that would be around 3.7 volts. And we also know that, well, for any battery, any rechargeable battery we wish to charge up, we will need to supply current to do so. Now, a lithium-ion battery has a little bit of a specific sort of current demand while charging, and you see that on this diagram. So initially, if you connect the battery to the charger and you would measure the charge going through the battery, or rather through the wires to the battery, you would notice that the battery would draw a lot of current, relatively speaking, in the beginning. Okay, so at this stage the battery will draw as much current, technically speaking, as it could. So you need to keep a really tight grip on the amount of current that runs through the battery, because obviously you can't have the battery sort of run away with the charger. Okay, so you really need to keep a constant current flowing to the battery. Now, while the battery is charging, the voltage will rise slightly as well. But when I say slightly, I mean only, say, 1 or 200 millivolts, not much more than that. Okay. Anyway, once the battery is starting to near its full capacity, so in other words, the battery is starting to be charged up completely, the current it will draw from the charger will start to drop off. Okay, and that is a rather steep drop off. So the current will relatively speaking rapidly start to drop to zero. Now, it never quite reaches zero. It reaches a point where the current it draws is about 3% of the current the battery is rated for. So say you have a battery pack which is rated for 2800 milliampere hour. If you reach 3% of 2800 milliampere, which is, I calculated it, 84 milliamp. At that stage, the rate of charging will slow so much that it really becomes useless to try to charge it up even more. Okay, so you can consider a lithium-ion battery charged when it draws about 3% of its rated current from the charger, and the voltage it shows is, say, not much more than 3.7 volts. Okay, technically you could go to 3.850 millivolts, but I wouldn't advise it. Okay, right. Now, they gave those phases a name, of course. I didn't find these out of thin air. Okay, so the phase where the battery draws a lot of current and you need a constant current charge is called the constant current charge period. Okay, so it's really this part of the graph. Once the battery is nearing its full capacity in charge, they call that the saturation charge period, and it's called saturation charge. Now, there is a question apparently which many people ask, and that is, how many times can you cycle a lithium-ion battery through a charge and discharge cycle? Okay, so say you discharge the battery with some application to about 30% of its charge, who knows, maybe even 90%, and then you charge it up again to charge it up to almost 100% of its charge. Well, that largely depends, of course, on the quality of the battery, and of course the number of times you discharge and then charge it back up again. Technically speaking, if you charge the battery up with less than or maximum amperage that it can deliver, okay, so say you have a battery that can deliver 2.8 amps per hour, so if you do not go over that amount of current while charging it, then you can probably charge a battery anywhere between 300 and 500 times. Okay, so the life cycle would be maximum, say, 500. If you charge it up with less current, you will raise the number of charge cycles a battery can go through. So, and that's what I will do. I built a charger which delivers only a fraction of the 2.8 amps the battery technically could charge. Now, if you do that, the life cycle would be something like 2000 times. Okay, so you would say, yeah, well, why don't we all do it then? Well, it largely depends on, again, on the application for which you use the battery. If you have a few hours to spare to wait until the battery is charged, well, then by all means charge it up slowly, or, well, with little current, and your battery will have a much extended life. If, however, you are in a real hurry and you say, well, you know, I really can't wait for 2 or 3 hours until the battery is charged, then you could go for its fully rated current. Okay, so, and by the way, you will often see on a battery a notation which says something like 3C or 4C, or maybe even higher, 7C. Now that capital letter C is really the unity charge. In other words, if a battery is rated for 2.8 amps per hour, C is 2.8 amps. Okay, so what they generally advise in literature is that you never exceed, say, 0.5 C, so 1.4 amps in the case of the 2.8 amps per hour battery. Okay, just for extending its life cycle as much as possible. Okay, but if you're in a real hurry, technically speaking, you could pump as much as in certain cases 10 times the current that it is rated for. And mind you, I'm saying current, okay, not voltage. But if you do so, the battery, of course, will become very warm and will have a much reduced life cycle. If you do it that way, don't be astonished if the life cycle of a lithium ion battery is a maximum of, say, 100. Okay, 100 discharge and charge cycles. So yes, lithium ion batteries are little miracles of power, but they are a bit of a high maintenance kind of stuff. Right, so that brings us to the charger. Okay, and the charger is right here. Okay, so this is the circuitry. It looks rather large, but really it isn't. And it is built around the well-known voltage regulator LM317. So let me show you. You have the LM317 over there, okay? And it's not a transistor, okay? It is in effect an integrated circuit, but in a transistor housing, and it only has 3 pins. Alright, so in effect what the LM317 is built for is to have a relatively speaking cheap and simple component with which to regulate voltage going to whatever is tied to its output. Now obviously in this case we have a battery tied to it, but it does need a little bit of an adaptation. Normally the LM317 is used as a invariable power supplies where you need a very constant voltage. Now, like I said before, lithium ion batteries need constant current and not constant voltage, which means that we need to modify a typical LM317 circuit to work or to function in that sort of way. So let me show you how. A battery to charge, and a lithium ion battery in this case, needs to draw quite a bit of current to charge up. And we do that by using, in this schematic I've drawn a power supply like this symbol here, which supplies a certain amount of voltage and a certain amount of current. Okay, and say the load in our case is the lithium ion battery, so there will be a current running through the load, okay, which is a sizable amount of current. Now, as you know, if you remember, if you look at the charge cycle of the battery, you need a constant current initially, say in, roughly speaking, in the first half of the charging of a lithium ion battery. In other words, you need a mechanism which will monitor the current which is running through the battery, so this current here, in an effective way, and use that to control, in our case, the LM317 to not dispense more current than we would wish it to dispense. How would we do that? Well, fortunately for us, there is a trick to do such a thing. Suppose you install a resistor, a rather large heavy resistor, in the circuitry which runs towards the load, or the battery in our case. The current that runs through the battery will also run through the resistor. And since the resistor has a certain value that we know, and in this case it is 10 ohms, then we can calculate a certain amount of voltage that runs, or that drops over the resistor. And we can measure that voltage. Okay, so if you put a multimeter over the resistor, you'll measure a comparatively speaking much smaller voltage than the voltage you see here. Okay, so if the power source delivers 9 volts, this will deliver far less voltage wise. Okay, so we're talking about the range of millivolts rather than volts. Okay, so what is the real trick, as it were? Well, the real trick is that the voltage you would measure over this resistor would be slightly more positive on this end and slightly more negative on that end. In the image you see that large resistor I was showing you a second ago, through which the current and voltage flows to the battery. Okay, so in effect the resistor, excuse me, you see there is this resistor on the schematic over there. All right, right. Now, like I said, so suppose that the resistor's input is this pin here, where you see the red crocodile lead, and you see the output of the resistor is here, where the yellow crocodile leads are attached. Let's see what sort of voltages we measure when we put our multimeter on both ends of the resistor. Now, this multimeter here is what we'll use. Okay, so let's see if I can give you a better view of it. All right. So the white crocodile lead goes to the plus of the multimeter. Oh darn. A silly machine. Okay. So the white crocodile lead goes to the positive of the multimeter. Now, okay, I'll put it to you. Which end of the power resistor through which the current is flowing to the battery would be its positive end, and which would be its negative end? Or would it have a positive or negative end? Well, let's see. Okay, so the yellow crocodile leads are those that go to the battery. So that is in effect the output of the charger. Okay, so let's suppose that is positive, all right, because it is attached to the positive lead of the battery. Okay, so I attach the positive lead of the multimeter to the output, and I attach the negative lead of the multimeter to the input of the resistor. Now watch what the multimeter will do. Yeah. So it stabilizes, say, around minus 52 millivolts. Okay, so that's what I'm saying. If you measure the voltage over this power transistor, which is in effect within a forming part of the positive lead of the charger, and you measure it in the direction we are measuring it now, then relatively speaking, the positive voltage would be slightly higher at this end of the resistor and lower at this end where the white crocodile lead is. In other words, if you measure it like this, yeah, it actually generates a negative voltage at this end. Alright? And that is exactly what we'll need to, say, steer the LM317 into outputting a constant current. Okay, now obviously now it's for the moment it's 62 millivolts that we measure. Obviously the more current the battery draws, okay, so the more current goes into the battery, the more current flows through the resistor, and due to Ohm's law, the higher the voltage will be that we will measure over it. Okay, so since the resistance is 10 ohms and never changes, something will change. So if the current flowing through it changes, the voltage level will change as well. And that's a very important fact. Well, that and its polarity. Now, just to show you, you don't have to take me at my word. Let me show you what happens when I switch over the ends. There you go. You get the same voltage, but now it's positive. So in other words, the voltage, relatively speaking, over this resistor is slightly more positive, closer to the output of the charger, and slightly more negative after it. Okay, so at its other end. An LM317, like I said before, has 3 pins, alright? And if you look at the front of an LM317, so it's front end because it has a metallic back, okay? But if you look at its front end where its labeling is, then you can say that the left pin is the adjust pin, hence the A label. The middle pin is the output pin, hence the O, and the right pin is the input where the raw DC plus goes in, okay, hence the I for input. Okay, so remember the LM317 is can only be used for positive voltages. In other words, you can only input a positive voltage on its input pin, not a negative one. If you want to do that, you need to use the LM337, not the 317. Right. So normally speaking, if you input a relatively speaking tiny voltage, positive voltage, to the adjust pin, you can control the flow of voltage that goes through the LM317, and also up to a certain point the current that goes through it. Right? Okay. Now the LM317, due to its construction, can never output less than 1.25 volts. So you can't use it, for example, to regulate any sort of voltage which would be lower than 1.25 volts, since it will always output at least 1.25 volts. However, it can go, depending on the manufacturer, you can buy LM317s that can go up to, say, 35, sometimes even 40 volts, but not more than that either. But typically I would say an LM317 can go to 35 volts positive on its output. And when I'm saying 35 volts, I really mean the difference in voltage between input and output. It can't be higher than 35 volts. Alright? Alright. Now, the output, as we all know, is directed through a power resistor, and then the output of the power resistor is hooked up to the battery. Now, there is a tiny voltage over this resistor. Okay. And like I said, the voltage on this end of the power resistor, so closer to the output of the LM317, is slightly more positive, relatively speaking, than this end of the resistor. Okay? So, if we can find a way to feed back that voltage to the LM317 adjust pin, we can use it to control the amount of current the LM317 lets through. So it could never run away, in other words, in current. Yeah, the current it would deliver would stay nice and constant, no matter how hungry, so to speak, the load would be that we attach to the power supply output. Okay? And what we will do in effect is we will take a little bit of that voltage, as it were, and lead it to the adjust pin. Okay? Now, remember I told you that we need a tiny positive voltage on the adjust pin of the LM to make it conduct more or less, right? Now, if we take a slightly negative or a slight negative voltage and we lead that into the adjust pin, we sort of bring down the amount of positive charge that goes to the adjust pin, therefore making the LM317 conduct less. Okay? Now remember, I also told you that the more current something draws, the higher the voltage will be over the resistor. Now we're still talking about millivolts here, but it turns out that is more than enough to do what we want to do, namely to automatically make the LM317 dispense just enough current to load the battery, but never too much. Okay, so by conducting a little bit of negative voltage back to its adjust pin, we can, in accordance to the current that's being drawn, tell the LM317 how much current to release to its output pin, right? And that's very important in a lithium ion battery. Remember, the lithium ion battery has a constant current charge phase. You need to keep it at a constant current, and that's exactly what, well, schematically, what the circuit would do. Okay, now this has an advantage in the sense that as the battery nears its saturation level, the current over the resistor will start to drop, and therefore the voltage will start to drop as well. And it's a linear thing, okay? So if the current drops, the voltage will drop, relatively speaking, as much as the current drops. If the current rises, the voltage will rise linearly together with the current that goes through it, okay? So in other words, as the battery is drawing less and less current, yeah, this negative voltage, which is being fed back to the adjust pin of the LM317, will drop, and ultimately it would drop to 0 if we waited long enough, okay? But we don't. We will wait until the battery nears, say, a very small current of 84 milliamps or less, okay? Right, so now that we know that, let's go to the circuitry. We tap off a little bit of the negative, remember, a slightly negative voltage we measure over the power resistor, that green resistor over there, and we feed it back into the adjust pin of the LM317. Now, that would be the end of the story. So if you cover up this part, you'd be there already. So this would be the charger in its entirety. Now, of course, that's not the end of the story. We wanted to make it a little bit more, let's say, useful. And how do we do that? Well, by measuring how far the battery that we attach to the output of the charger is in its charge cycle. And we measure that by using a special little IC, which is called a KA2284. Now, by the way, there is another IC on the market which is quite similar to the KA, but it has the serial or the type number NA6884. Okay, so either a KA2284 or an NA6884. Okay, they will both do more or less the same thing. Now, what this chip really does is it measures a certain voltage that it gets, yeah, and in accordance to the voltage that it measures, it will light up one or more LEDs, well, actually none or more LEDs. Once it gets a full voltage at its measurement pin, all the LEDs will light up. Okay, so what we do actually is we tap off a little bit of the voltage that is used to adjust automatically the flow of current through the LM317. We take a little of that voltage and we measure its change with the KA2284. And that's what's happening right there. Okay, so now for the moment you see 4 little red LEDs light up, and you see that big LED on the right, which is in effect a green LED. So the KA2284 is rigged in such a way that when the battery draws only very little current, so the battery is loaded almost to capacity, the voltage, which will be measured by the KA2284, will be at a maximum. And at that moment, not only the 4 red LEDs will light up, but also the green LED. So once the green LED lights up, you know the battery is charged, and you can decouple it from the output of the charger. Okay, so really that's it. Now don't pay too much attention to this part, okay? I had the intention of building this as a sort of a warning mechanism to warn me whether the battery would run hot or not while I'm not looking at it, but I thought the charger works perfectly as it is, so there is no real need for this, okay? Still, if you would feel if you would feel safer to have a mechanism that would tell you the battery runs hot, then you can still build this if you like. Now the point would be, of course, that the NTC, which you see in the schematic, would be connected somehow to the housing of the battery, okay? And this would be calibrated in such a way that once the temperature of the battery would run higher than, say, body temperature, or a bit lower than that, maybe 33 degrees Celsius, so slightly warmer than room temperature, then the alarm would start to sound, and it would give off a rather loud, shrill tone, yeah, which is guaranteed to draw your attention, okay? But like I said, I didn't build it, and I don't intend to build it for myself, but if you want to, then be my guest. Anyway, that's it for the internals of the charger, and the only thing I want to show you is the parts list when you're going to build the charger. Now I used 4 3mm red LEDs and 1 5mm green LED. If you want to use a different type of LED, be my guest, okay? So the color really doesn't matter that much. However, I did notice that the green LED draws much more current than the little red LEDs, and the voltage at which it lights up is slightly higher as well. Therefore, on the schematic I drew these 2 resistors, okay? So this resistor here drops the current a little bit for these, and voltage for these red LEDs, these 4, the first 4, okay? And this resistor here drops the voltage and a little bit of current for this LED here, the green one on the right. Now it all depends on how bright you want the LEDs to light up, okay? So if you want them to be less bright, well, obviously you would make these resistors higher in value. If you want them brighter, you would make this less high, okay? Then you would drop the values of these resistors a little bit, okay? And when I say a little bit, I really mean a little, okay? So you could drop this one to, say, 150 ohms, and this one, say, somewhere around 70 ohms instead of 120. Alright? Right. Now remember, you have 4 LEDs connected to this resistor, this resistor will get pretty warm. So you better use a power resistor. I use a 1 watt resistor, which still gets a bit warm. I would advise maybe to use a 2 or 3 watt resistor instead, depending on what you have, okay? But 1 watt will suffice, although it will run a bit hot. Right, that's it. So the last thing to do for me now is to transfer the charger you see there to a PCB, and that's exactly what I'm going to do next. I'm transferring the parts to the little breadboard PCB, and as you can see, I mounted already the rectifier bridge, so the full wave rectifier bridge, and a filtering capacitor. Now, something which I did not indicate on the schematic is that I also built a small, you could say, friction contact, or rather screw contact, on the PCB. Okay, and in fact this contact will be used to connect up the secondary of the transformer. I also mounted 2 wires on one of the AC pins coming from the contact, and one of the AC pins of the rectifier bridge, which is marked by a little squiggly wave. You see it there. Okay, so in effect these 2 wires will be led to a small interrupter, something like this, a small switch, yes, which will be used to to switch either on or off the charger. Okay, and I effectively put the switch on the AC and not the DC, because I want to completely switch off the charger, so totally. I do not want any sort of voltage remaining on it. Alright, I mounted the LM317 to the heatsink, and I showed you the steps that I took to do that. And as you can see, it's quite solidly secured now to the heatsink. Now, a couple remarks. Don't be too skimpy on the heatsink paste, okay? I'm not saying you have to go totally overboard and cover it in a thick layer of heatsink paste. That won't help, but you still need to generously coat each side that makes contact with the next one, and so forth until it makes contact with the heatsink, because obviously the more surface you coat with an even not extremely thick coating of heatsink paste, the better the heat will be transferred to the heatsink, and that's exactly what we want. Also, you can see the screw is perfectly insulated from the metal body of the LM317, so it'll never make contact, I mean electrical contact. Okay, so if there's a little bit of heat paste being squeezed from under the LM317, that's okay. As you can tell, it's not like it's flowing off all the sides of the heatsink. So I used a generous but not exaggeratingly so dollop of heatsink paste. And this is the final result you should have. There are two things that I want to tell you, or maybe even three. The first thing is, when you assemble something like this, try to resist the temptation of wanting to test it immediately. Okay, I know it's tempting to connect it up and then to fire it up and see what it does, but we're all fallible. Okay, we all make mistakes. So rather than giving in to your urge to fire it up, check first whether all the components are connected correctly, because excuse me, trust me, a mistake is quickly made, and you wouldn't want to blow up a nice design, wouldn't you? Now, the next thing I want to say is that you should also strive to keep all your components leads as short as possible, and put the non-critical or non-heating components close together. Okay, the shorter the leads, the less noise you will introduce into your design. Now obviously parts that get hot or could get hot should not be crammed in between all other parts. Okay, so those parts you rather keep at the outside of the PCB like I did. Okay, so this part heats up, this could heat up, I'm not saying it will, but it could, and this resistor here heats up as well. So I mount those, and oh yeah, the rectifier bridge gets warm as well. So I mounted those parts at the outside of the PCB where they get sufficient ventilation. Okay, and the third thing I need to tell you is that while I was building my battery charger, I noticed I had forgotten to correct the values on the schematic which I showed you earlier. So you'll find a corrected schematic somewhere at the end of the video. Okay, anyway, that's it. Let me check it first, and then when I'm ready checking, we'll fire it up. Before I start explaining how you calibrate it the way it is, I should give you well, a little bit of a warning perhaps. So you'll remember I told you that when you build something and or design something, you should always take your time to check for errors before you test it actually, and of course also before you put it together. And well, my own advice came back with a vengeance and bit me in the rear end, so to speak, and I got a little taste of my own advice, because I'll tell it to you frankly, I was hoping to be able to cut some corners and gain a little bit of time in order to publish my project. But well, like I said, it came back with a vengeance, and it really bit me, unfortunately, I would say. So yeah, let me explain. So when I was putting this together, I did it all in one go. Okay, so I built the whole device in one single pass. And I was rather confident that I hadn't made any mistakes, neither in my schematic nor in the way I built my charger. But it turns out I did. Of course I did. It took me a heck of a lot of time to put my mistakes right. So the time that I may have gained putting it all together in one go, I quickly lost in trying to debug the whole device. Well, I say trying, I did debug it in the end, but well, any time gain I might have had putting it together quickly, I lost just as quickly in trying to figure out what had gone wrong. So, to make a long story short, when you're drawing a schematic, you should always check it for errors. And I can tell you now rather confidently that the schematic you're seeing here is the right one. I mean, it's error-free. All the values you see are the correct values. And well, I checked it and it works. Okay. Also, I straightened out a few errors I had made while building the charger, and here as well what you see is the definitive version of the charger. So there are no more errors in it any longer. Okay, so that being said, if you build this exactly the way I built it, I will say you do it at your own risk, because the parts that you will use or buy might not be exactly the same parts I use. So therefore, tolerances might be different, values might be slightly different, and therefore your charger might not be working exactly the same way mine does. But if you stick to the values, I think you shouldn't have too much trouble making your version work correctly as well. Now we come to the point which most people dread, which is that you need to calibrate your device. Yeah? And before you truly start to calibrate it, my first advice is that you simply switch it on. You know, I built an on-off switch to it, and you check it. You see whether it works or not. Yeah, and as you can tell, at first glance, it works. So, what will you need to calibrate your charger? You will need a multimeter, like that one. You will need an extra 10 ohm resistor, like this one. And you will need a small screwdriver, something like this, okay, to turn the potentiometers, and there are 3 of them, on the charger. If you have those 3 tools, you should have no problem in getting it to work correctly. You need your multimeter close at hand. The first thing you need to measure, okay, are the unloaded values, so these values here, okay, and there are 3 points that you need to take into account to do that. If I show you on the schematic, it are the points A, B, and C you see on the schematic, Okay, so this is the output of the battery charger. This is the coupling between the potentiometer and the resistor that goes to the base of the sensing transistor. Okay, so this point here is important. And then you have a coupling between the potentiometer and the resistor going to the input of the display chip, okay, the KA2284. And to be more precise, this potentiometer is connected with the swiper to pin 8 of the KA. Okay, so those are the points A, B, and C, and they correspond with 3 potentiometers on the board. So, well, actually 2, I should say. So this one here is the potentiometer at point B. This here is the potentiometer at point C. This one is a potentiometer which sets the output voltage when unloaded. Okay, so I repeat, when there's no load on the output, so the output here of the battery charger. Okay, so right, there you go. Now, the very first thing you need to do, and I'll try to make, okay, like this. Okay, so the very first thing you need to do is to measure the output voltage of the battery charger with no load. So here we go. Okay, so now the battery charger output reads 7.51 volts, which is a tad too low. I like to set it to 7 volts 55, and which is exactly what I'm doing now. So okay, so that potentiometer, I will turn it. There you go. Oh, that's a bit too much. There you go. 755 or thereabouts. You have a tolerance of a few millivolts, I should say tens of millivolts. Around 755, in my opinion, is ideal. If you want to push it a bit, you can go all the way up to 765, but that would be really pushing your lithium ion battery hard. So I would go to a voltage somewhere between 755 and 760 and not much higher. Okay, so that's the voltage at the output. Now the next thing you need to measure is the voltage. So that's the voltage at point A. Now we go to point B, and point B is the point between the potentiometer and the resistor connected to the base of the transistor, and that should read about 7.1 volts. In this case it's a bit lower. Like I said, it can vary a bit. It can vary, say, roughly, well, I'd say 50 millivolts, either up or down, around 7.1 volts. Okay, so it's not extremely critical, but you should get a voltage of around that level. Okay, still unloaded, so there's no load attached to the output. Okay, so then we move on to point C, which is the point between the potentiometer and the resistor going to the input of the KA2284, which is right here. Okay. And you should get about 0.6 volts. Okay, so as you can tell right now, I'm 30 millivolts below that. No, what am I saying? I'm 3 millivolts below that. Okay, so a value of about 0.6 volts or 600 millivolts is right. That's what it should be. Okay, so that's all unloaded. Now you disconnect this again and you reconnect your multimeter to the output pin of your battery charger. So there we are at 7.55 volts. So now you take your extra 10 ohm resistor, power resistor, and okay, so you attach, of course, the negative of the battery of the resistor to the negative output of the charger, obviously, and you connect the other pin of your resistor to the positive. Now watch the voltage. Okay, so the voltage immediately drops and you also see the LEDs switching off. Yeah, well, at least the number of LEDs switch off, and you should get a output voltage, so at point A on the schematic, of around 1.8 volts. Now that can vary a bit. It can be 1.775 and it can go all the way up to 1.820 millivolts. Okay, so it should be anywhere around 1.8 volts and not much higher or not much lower. Alright? Alright, so ideally speaking, if it's around 1.8, 1.81 volts, that's perfect. If it's a bit lower like it is now, still no problem. Right, so now you move the multimeter from point A. Oops. Now you move the multimeter from point A to point B, okay, which is the attach point between the potentiometer and the resistor going to the base of the sensing transistor. Here we go. Now, in loaded conditions, okay, when you attach a load to the charger, you should get about 4.07 volts, right? And this is where the second potentiometer comes in. Okay, so if you see a much too high or much too low voltage, you can adjust the voltage by turning this potentiometer right here. Okay, this one right here. You should get around this voltage, and again, this is plus or minus, say, 50 millivolts. Okay, not much more, but if you read 4.1 or you read 4.0, that's fine as well. It can vary a little bit according to the temperature in the room and everything like that, but as long as you stay within this value, you're safe. Okay, so now do watch the LEDs. So if I disconnect the load, you see all the LEDs switch on. If I put the load on the output, you see that the last three LEDs, if we read them left to right, okay, the last three LEDs are almost off. I mean, they are still on, slightly on, but it's so faint that compared to the two on the left, well, you could say they are practically off. Okay, I know it's a bit annoying, but it has all to do with how the KA2284 works internally. It's not an extremely accurate chip, so there's a little bit of jitter on the readout. But if you see something like this, that's okay. Alright? Alrighty. Now, the next thing you need to do is, oh darn it, okay. The next thing you need to do is you move your multimeter to the connection point between the potentiometer and the resistor that ultimately go to the signal input, so pin 8 of the KA2284. Okay, so here we go. I connected. Okay, and there you go. So you should get a voltage of about 315 millivolts, okay, or 0.315 volts. And if you're around that value, you're fine, you're just fine. Okay, so, and again, the tolerance here is, oh, I'd say, roughly speaking, 20 millivolts either up or down from this value. Okay, so if you measure 3.3 or you measure if you measure 330 millivolts or you measure 290 millivolts, well, that will probably work just as well. Now there is one thing that you should notice. When the load is attached, so the 10 ohm resistor you see over there, okay, so this one, then the LEDs should burn pretty much like this. If they don't, then you need to adjust this potentiometer on the right, this one here, okay, and you need to turn it left or right until, with the load attached to the output of the charger, you see the LEDs burn or light up more or less like this. So the two on the left fully on, the three on the right very faintly lighting or not at all. Okay, and you can adjust it by turning this potentiometer here. Alright, so this one here. Now, no, I'm not going to turn it because it's quite fiddly, okay, to do this. Now, the thing is, you might not succeed in making it work the very first time, because the potentiometers are often in a wrong position when you mount them and all that. I mean, they are incorrectly set, okay, so you might need to go through that cycle 2 or 3 times, okay, always starting at point A, or rather, yeah, point A you could say, and starting with the potentiometer which sets the output voltage of the charger, so this one here, okay, and you always go counterclockwise like this. So when you don't get it the very first time, you start all over again by setting the voltage unloaded, okay, then measuring all the voltages on point A, B and C, so A being the output, B being the connection between the potentiometer and the resistor that go to the base of the transistor, and point C being the connection between the potentiometer and the resistor going to the input of the KA2284. So in effect, you measure these voltages, okay, in unloaded state and in loaded state, and you always go from A to C and always counterclockwise, okay, so you move always counterclockwise on the potentiometers. Normally you should get it right, I'd say after 3 or 4 passes at the most. You should be able to get it right. Now, if you don't immediately manage, don't panic, okay? So if you're not sure in which direction you're turning the potentiometers, then you could turn the potentiometer C, so the last one, the one on the right here, okay, once all the way to the right and once all the way to the left. And of course, being careful that you attach a load, you must observe whether the LEDs react the way they should, okay? So with the load attached, the two or let's say the 3 on the left on, the 2 on the right off, or nearly so. I mean, the green LED is slightly on, but the camera is so sensitive that it looks brighter than it is, okay? So when I look at it with my own eyes, I can barely see any green light coming out of it, you know, and the fourth LED, the red one, and the third one is so faint that I can't see it with the naked eye. But the camera is sensitive enough, so it picks it up. Anyway, if you've done this whole cycle, then you're there and you're done. And this is the finished product, put into its own little case, which is plastic, and all connected up, ready for use. And I used eyelets to connect the transformer. Okay, so there you go. This is the transformer and these are the outputs. The only reason why I did that is because I want to use the transformer for other purposes as well. So instead of buying tons of transformers, I just built in my charger itself into a little case, which is just a plastic box I recuperated somewhere, and I'll place the transformer outside of it. Okay, maybe I'll build its own little enclosure later on, but in any case I want to keep both separate so that I can use my transformer for other purposes. So there you go, a completed charger for lithium ion battery pack.